think I can start. Hello everyone. Not sure what to do today. So many things I have to cover. Like, um, there are some of the core subjects from computer science which I have not studied yet, and apart from that, I I have not covered cache memory and just memory in general in computer organization and architecture. Of course, most it is mostly from organization, but um, yeah, it is still pending. So hopefully today I cover it and get some things off. So again, this is not planned. I did not plan much for today, but let's see. um, I'm just checking some of the sub pending topics on my phone. Like, there was a PDF which I'm taking as a reference. So let me check once. Mm, RAM, flash, and all this stuff. Um, okay. How can I find this? Actually, this is, I'm seeing one question, and it is mostly about it has given me three implementation of C code, and it has told me like which program section, the which section is associated with which type of storage. Like, dot data section is uh, has the targeted memory as L2 RAM. Similarly, BSS section has L1 RAM. So on that, this is a sample question, and it is telling me like which implementation would be best. It of out of three implementations which all do the same thing but in a different manner. So this is interesting, but I don't really know how to cover it. But let's see. So okay, so I think first of all I do need to cover memory, right? Without covering up memory, I don't think I can progress any further, at least on this topic. So maybe I should cover cache memory, memory in general. I think, of course, I'm saying cache again and again because in the interview I have heard that they ask a lot of questions about cache memory, but I will just write memory in general. Let me increase the size as well. How does it look? Oh, of course, it won't be visible such way, but regardless, let's leave that. But okay, so I will be covering memory today a little bit more, I think. Yeah. uh, Apart from memory, uh, again, I have finished embedded C part, struct size calculation. Yeah. I can bit manipulation. Yes, I can do that as well. Memory layout of C program. Yeah. Static and volatile. Okay, I'm confident with that. Compilation stage. Yes, I'm confident with all these topics. So these topics won't be the problem. um, Neither will be the data structure part, because in C programming, at least, the questions which they are asked are not that complicated for me to cover. So it will be fine. It won't be way too difficult for me, so I think I can skip this much. What I can do right now is multi-process synchronization techniques. And again, this is, I don't really know what exactly this is. Multi-process, again, I think this is mostly like a scheduling thing, how things are scheduled. But I don't really know if they even ask questions on this, like multi-processing synchronization techniques. Yeah. Apart from that, I think these two in themselves are really big topics, so I think just doing this much will be taking a lot of time for me. If I make even a little bit of time, I will look into DBMS a little bit. DBMS or SQL will be something I will be debating on, like whether I should do DBMS or just plain SQL for now. But yeah, this should be basic plan for now. Again, I won't be doing this completely. I will be doing just this. I will just get this started. But for these two topics, I will try to cover as much as I can, uh, because interviews are coming. But again, I don't really think I can go that much deep. I cannot go extremely deep into these topics, but for whatever depth I can go, I will try to cover. I will try to cover these topics, and I think I will be streaming a little bit for a little bit longer today. So let's see. Where was I? Again, let me see how the stream is going for now. Um, yeah, this looks nice enough. It should not be a problem. So whatever it is, let us get started. First off, memory. Let me look up some resources for way to start learning memory, just enough for me to get an idea at least. Let me ask this for resources. I think Grok has really nice suggestions for all these things. As much as I tried it, I did not try it that much, but for whatever I have, let's go for it. What should I topic? Topics to cover, to learn about memory in computer. Architecture and organization to a point which is just enough to cover for an interview. Again, this is how I think I should get started, because I do not have that much time to cover each and everything. But yeah, let's see the response. Memory hierarchy. Okay, I will look into this. Cache memory, cache mapping techniques. Okay, replacement policies. Yeah. Main memory, RAM, virtual memory. Okay, I don't think I will need to go till virtual memory and stuff, but these first three topics look nice to me, so I will just take them and copy paste somewhere. So if I have to reference back, I think I can look over here anytime. So memory hierarchy. Let me check for resources for memory hierarchy. I think I should increase size for this as well, but not for now. When I will read into something, I will. Let me also look for memory hierarchy and its characteristic. Maybe this will this be enough for me to cover everything? Wikipedia. Now this will go way too deep, way too deep for me. I don't think I can cover all that, but let's see. Okay, this is short, but will this be enough? Okay, this is way too short for me to even discuss something on it. I think I will just read it and pass through it. I think this, again, this is also not that much. Maybe I need, maybe this is just an introduction and I need to go into that to, as I cover each and every topic, right? So I think this is fine. Again, this also has some resources. Maybe I can learn more from this. So what does this come under? Because I was recently studying about instruction pipelining as well. So this is pretty nice that I have all these side by side, because even it has interrupts and DMA. Let me check if I have to cover interrupts and DMA as well. Um, Interrupts and DMA is there, but I don't think it is for me. It is, again, it does not come as a topic under computer architecture, but it does come as a topic for microcontrollers. So I don't really know about that. Maybe I can study and cover microcontroller tomorrow. Let's see. Again, I have not been very consistent with going live and studying recently, because I have not been feeling that much good recently. I don't know why, but let's say probably a melancholy, but things, it is not that bad. It will be fine. So I think I can get started. Memory hierarchy design and its characteristics. In computer system design, memory hierarchy is an enhancement to organize memory such that, let me increase the size. Memory hierarchy. In computer system design, memory hierarchy is an enhancement to organize memory such that it can minimize the access time. Yeah. Memory hierarchy was developed based on a program behavior known as locality of reference. Maybe this comes later. I will just keep it open. Same data or nearby data is likely to be accessed again and again. The figure below clearly demonstrates different level of memory hierarchy. Okay, yeah, I've seen this diagram. Memory hierarchy helps in optimizing memory available in the computer. There are multiple levels present in memory, each one having different size, different cost, etc. Some types of memory like cache and main memory are faster as compared to the other types of memory, because they are having a little less size and are also costly, whereas some memory has little higher storage value, but they are little slower. Yeah. Accessing of data is not similar in all types of memory. Some have faster access where some have slower access. Type of memory hierarchy. This memory hierarchy design is divided into two main types, comprising of magnetic disk, external memory or secondary memory, comprising of magnetic disk, optical disk, and magnetic tape. That is peripheral storage devices which are accessible by processor via an input-output module. Okay, yeah. Okay, this is literally just as long as there is input output module, like I think from input output module it means UART, SPI, I2C, all those stuff. Again, let me cross check this once. What exactly is IO module meant by here? Is it UART, SPI, I2C? I think it is USB and all those stuff. Okay, at hardware level output module uses protocols like this, but these are just communication interfaces. Input output module is broader concept that includes controllers and device drivers. Okay. Software that manages the hardware, disk controller and tape controller. DMA controller allows peripherals to access memory without CPU intervention. Wait, okay, this is not really clear to me. I think I should start over. An input output module is a bridge between CPU and peripheral devices. It handles data buffering, error detection and control, protocol conversion, translates signals between CPU and peripherals. Okay. Device addressing, help CPU identify which okay, got it. It is so okay, this is pretty clear that there is not much to cover in it. This is just a simple buffering for just like we do for audio and stuff, right? We like prepare audio just beforehand and store it somewhere so that it does not always get generated in real time. Like it does not need to be real time. It can be generated beforehand as well, so that there is less chances of any errors, right? So that data buffering is clear from that. Error detection and control checks for transmission error. Okay, this is just for this is probably going to handle fallback and stuff, that what if something happens, then do this thing, or error detection and stuff. Okay, sure. Protocol conversion translates signals between CPU and peripheral. Okay. Device addressing, this is probably like a mapper and stuff. So that mapper, probably a mapper, because it is going to tell which device is going to be active. So is input output module UART, SPI, I2C? It depends on level of abstraction. Low level, at hardware level, input output module uses protocols like this, but these are communication interfaces. Input output module is a broader concept that includes controllers, disk controller and tape controller. Okay, so it is probably the thing which is reading the input output from the actual physical thing, right? So this is that. And the device drivers, the device drivers are just to translate whatever is being read from these controllers to something which the software can understand. High level, from system architecture point of view, in computer architecture, the input output module is abstracted as DMA control, direct memory access. Let me move my lab first. DMA, direct memory access, allows peripheral to access memory without CPU intervention. Okay, this is specifically the thing which I am not able to understand. Why would why and how? Why is this necessary, and how is, again, I know, I can see why this is necessary, but I don't understand how this is going to solve that issue. Like, it is not that is my question. So why is this necessary, and how it solves the issue? Write in simpler language, because I cannot go deep into a rabbit hole right now. Imagine your CPU is a busy manager who has to handle everything: calculation, running apps, and even moving data from RAM and hard disks. USB. Okay. Yes. Without DMA, even every time a disk or USB drive needs to transfer data to RAM, CPU has to stop its work and manually move each piece of data. This is so slow and inefficient because CPU is interrupted frequently, like micromanaging every small task. CPU could be doing more important tasks like running program. How DMA solves this problem? DMA is like hiring a special assistant whose only job is to move. Okay. CPU gives instruction, tell DMA copy 1 GB of data from hard disk to RAM at address X. DMA takes over. Okay, got it. So it is like a parallel task, I think, which runs alongside whatever CPU is telling it to. So it technically, if you are copy pasting a large chunk of data, so not just large chunk of data, any chunk of data, or just doing something with the memory, it tells it to do something alongside. So that is how I think I can understand that. DMA takes over, CPU keeps working, does other tasks, but DMA does the heavy lifting. DMA notifies CPU when done. Hey, boss, transfer. Okay, sure. So I think this part is important. This is something which I was wondering, but I did not say. Like, could it not be an issue when CPU suddenly asks to provide me, like, to provide CPU asks to access value at the location it just put the value in, but I think this answers it that CPU probably will block or something like that will happen, or probably take reference from there must be some internal compiler optimization, right, to handle this thing, but this probably answers it. So yeah, well, DMA necessary faster transfers, yeah, less CPU overhead, sure, better performance, apps run smoother because CPU is not constantly interrupted, yeah. So it is like a but not yeah, it is somewhat like that. Got it. So I think I'm clear with that now. Again, where did I even start for this? I forgot. At high level system architecture, yeah, input output module, right? So input output module will even have this specific section. It will have input output processor. Okay, yeah, again, these things are specifics, right? Southbridge, okay, these things are very specific, but I don't think I need to go into that, but at least this much part is common, so I think I can visualize what is being said. So this much done. Internal memory or primary memory, comprising of main memory, cache memory and CPU register. This is directly accessible by the processor. Okay, yeah, got it. This will probably RAM register. RAM is meant by this, obviously cache and CPU registers here. Memory hierarchy design. Okay, let me look into this one. Increase in capacity and access time, and increase in cost per bit. Yeah, it is. Yeah, it probably answers that. So memory hierarchy design. Registers are small high-speed memory units located in CPU. They are used to store most frequently used data in instructions. Registers have the fastest access time and smallest storage capacity, typically ranging from 16 to 64 bits. Once again, registers are small high-speed memory units located in CPU. Registers have fastest access time smallest storage capacity and typically ranging from 16 to 64 bits. Yeah, sure. Cache memory is small fast memory located close to CPU. It stores frequently used data instruction that have been recently accessed from the main memory. Cache memory is designed to minimize the time it takes to access data by providing the CPU with quick access to frequently used data. Yeah, that is right. And main memory, also known as RAM, is the primary memory of computer system. It has larger storage capacity than cache, but it is slower. Yeah, that much is okay. uh, Static RAM stores the binary information in flip-flops, and this one is probably, yeah, it's a capacitor, and this is probably slower or something like that. What I heard was this is not that efficient and this is more efficient, something like that. As far as I remember, it requires refreshing circuitry to maintain charge on capacitor after a few milliseconds. It contains more memory cells per unit area as compared to SRAM. Yeah, this is faster. Yeah, this is faster, and but you can accommodate more with DRAM is what I think. So SRAM is faster and DRAM is usually larger. Am I correct? Yeah, sure. Let me peek into this for once. Chip select read write here, 7-bit address, sure. DRAM, SRAM. Okay, I don't think I will be needing this, but secondary storage such as hard disk drive and SSD, yeah, is non-volatile memory unit that has, yeah, this will just retain its value. Slowest access time is typically the least expensive. Yeah. Magnetic disks are simply circular plates that are fabricated with either metal or a plastic or a magnetized material. Magnetic disks work at a high speed inside computer, and these are frequently used. I don't really know that much about magnetic disk. What I know about is magnetic tape. Magnetic tape is generally used for backup of data. Yeah, in case of magnetic tape, the access time for a computer is little slower, therefore it requires some amount of time for accessing the strip. Okay, yeah. So I think this much is covered and pretty much clear to me. Again, I hope I don't mess this up. I hope I don't interchange both of these topics together, but I will mark this up just in case. So where do I even write it? Have I studied it earlier or not? I have not, so I think I can just write fresh right now. For memory, what did I cover till now? Memory hierarchy was the topic here. Memory hierarchy was the topic, and yeah, what I looked into was internal and externals, and what the difference was probably the input output module was required, right? So I think that is probably the only point which I need to write. Yeah. So with this, I think I can elaborate input output module more clearly. Input output module comprises of all those protocols which are being followed, for sure. Protocols, the thing which is handling these protocols, um, something which handles these protocols, and um, uh, from where these things will get their data. So that will be controllers. Controllers, and am I missing something? Am I missing something from these topics? Controller, and yeah, drivers. Something which handles these protocols is drivers only. So I think that is it. That is enough for me to cover all which I need to explain for memory hierarchy. So I think I can move on from that. Registers, yeah, this is not really that big of a deal. It's something I would expect. I don't think they are going to ask something in too much depth about how these registers are implemented and stuff, but I think this should be enough. Cache memory, again I will be reading cache soon enough in much depth, so that is fine. Main memory, yeah, I know the difference between static RAM and SRAM and DRAM. Static, I don't know what static uses, but I know DRAM uses capacitor, which makes it a little bit slow, that it requires a little bit of time to refresh itself and continue working with new data. So so it is slower, but it can have more space, like it can accommodate more memory. So that is it. And static RAM does not require that. It does not require capacitor and stuff. That is all I know. But what are static RAMs built from? Transistors are used. So this transistors are not used for this. Okay, sure. Refreshing unit, it has a refreshing unit. SRAMs are expensive. Low density device, yeah, okay, this should be enough. No, this should be enough. I think what I know is enough for now. Secondary storage, yeah, again I did cover this. Secondary storage, technically all these are also secondary storage, kind of external or secondary, because regardless, these three will require something like an input output module for me to read the data, do some input output with all these stuffs, right? So yeah, I think this much is enough. Characteristics of memory hierarchy: capacity, access time, performance, cost per bit. Okay, access time, performance, cost per bit. Access time, yeah, I think both are kind of interrelated. Capacity, yeah, again I don't think I will note this down. this is self-explanatory. Maybe I should so that I have something written in my copyright, so I don't feel like I have not covered anything so far. So characteristics of memory hierarchy, and in this uh, what is there is capacity. Apart from capacity, what do I say, performance, access time, both these are, I think both of them are same, so I will just skip that. And the last one is cost for sure. So yes, this should be enough. I think I can move on with that. System supported memory standards. Access time, yeah. Cache, sure. Main memory. And bandwidth, okay. Oh, what? So what is bandwidth exactly? Managed by compiler, hardware, operating system. Yeah, okay. um from here, yeah, for sure. Like what really is um, bandwidth of memory standards, right? These are one name of, or I should just address, like I should just call it as memory. Bandwidth, for what exactly is meant by bandwidth of memory? Again, am I streaming? How is it going? 37 minutes, and like, yeah, it looks like I am. Bandwidth is the maximum amount of data that can be transferred to or from per second. Yeah, got it. So that is nice. This is related to this, probably access time, so that should be fine. Advantages of memory hierarchy, cost of, yeah, all this stuff, I got it, I understood that. I think I should define memory hierarchy um, much more properly, right? What I explained the way in my notebook is not enough, so I think I should write it again. Arranging memory is arranging memory for CPU to access in such a way that it is optimized for both performance and the cost efficiency. Right. Is my pen paper even visible to anyone when I write something? But yeah, that is it. um, I think this is a pretty nice explanation. Wait a second. um, Okay, I'm back. So I think I can continue. So where was I? Mm, the cost efficiency, optimized resource utilization, efficient data management. Okay, I think I should add this. And optimized yeah, this is fine, this will work. Disadvantage, yeah, complex design. Again, how can this be both if you are saying it like that? I don't really know. Latency, of course, if you are buying something, you are not getting it for free, right? So how can this be advantage and disadvantage both at the same time? um, Latency, accessing data stored in slower memory increases the latency, yeah, but yeah, got it, there is not much to argue. Maintenance overhead, managing and maintaining different types of memory adds overhead. Yeah, this is actually this actually comes under complex design as well, like complex design, complex implementation. But yeah, both complement, both the topics are complementary to each other. So yeah, how long is this is, I think I will be able to cover at least this much of it, right? So this is the data, that is pretty nice, that will be pretty nice. So yeah, cache memory in computer organization. Cache memory is small high speed storage area in a computer. It stores copies of the data from frequently used main memory locations. There are various independent caches in a CPU which store instructions and data. Yeah. The most important use of cache memory is that it is used to reduce the average time. Yeah. Concept of cache works because there exists a locality of reference. Yeah, that is true. I think I should note that down. In cache memory, what was I going to write? First thing was like first thing should be there that cache is pretty cache stores copies, right? It is cache stores copies, it does not keep the memory to itself, and does is cache is not really making the memory exclusive to cache, it is just storing the copy of it. So I think I should write it that way. uh, Stores copies, yeah, that will explain itself. Stores copies, works on presumption, is that what you call? Works on assumption that works on providing frequently access memory faster to processes. By storing this information closer to the CPU, cache memory helps speed up the overall processing time. Yeah, much faster than main memory. Yeah, when CPU needs the data, it first checks in cache. Yeah, I should add that. Uh, CPU first checks in cache. Um, Extremely fast memory type that acts as a buffer between RAM and CPU. Okay, now holds frequently. Okay, costlier than my speed. Yeah, this is just repeating itself. It is a type of memory in which data is stored and accepted that are immediately stored in the CPU. Wait. Okay. Yeah. I did not read it with full focus, but it is a type of memory in which data is stored and accepted that are immediately stored in the CPU. Most commonly used register is accumulator program. Yeah, all these. Level 2 cache memory, level 2 or cache memory. Again, why am I looking at this specification? Like, did I not cover this just before? Why is this so repeating itself so much? But again, I think this is where it starts. So when the processor needs to read write, it first checks again if the processor finds the memory location in the cache, a cache hit has occurred and data is read from cache here. If processor does not find memory location in cache miss has occurred, and for cache miss, cache allocates new entries and copies in data from main memory. Okay, so what is happening is processor first looks into cache if it finds the thing in cache, if it finds the thing in cache, then it will just return itself in the CPU, and else it will just go fetch it from the memory. Cache misses, then it will go to memory, RAM probably, a RAM or just memory in general. I should write it memory, right? I think that will be wise. And memory will first return data to processor and cache. Right, this is how it should go. Data sent to both CPU and cache. So yeah, this is nice. So this much is clear. Performance of cache is, again, this is just ratios, I will not look into it. We can improve cache performance by using higher cache block size or higher associativity, reduce miss rates, reduce miss penalty. Again, I think we will be covering all those topics right now. So in those topics, cache mapping, I think I have to look into again. Let me look from above what is here in this topic. But again, I think this is the only thing in this section what is here in cache organization. um, okay, wait. um, yeah, I think I have to properly cover these three topics. I cannot rush anything. So cache mapping is the next topic. For cache mapping, there are what is cache mapping? Probably the way in which caches the layout of caches uh, refers to method used to store data from main memory into cache. Determines how data from memory is mapped to specific locations. How memory from main memory is mapped on the cache. So if CPU asked for a certain address, how will cache provide the data for how will cache even determine whether it has data for this specific memory address or not, or if it has that, what is the how can you even access that memory address in cache? Because the memory address will not be something which will be native to cache, right? It will be something which is more compatible to the memory main memory, right? So there is a middle something mapper or something, again mapping, that is what we are learning. So now a mapper will be something to direct these requests to the point where the memory is stored. So that is how I think it works. Again, that is how it works. Why am I even assuming that? But I think we can move on from there. Direct mapping, fully associative mapping, and set associative mapping. Direct mapping, again first type. I will note that down. Direct mapping. In direct mapping, the first thing which I have is, what is it? Direct mapping is a simple and commonly used cache mapping technique where each block of main memory is mapped to exactly one location in cache called cache line. Wait, what do you mean by block? Like, again, I will assume it as segments, but what exactly are blocks of memory? Is mapped to exactly one location in cache called cache line. If two memory blocks map to same cache line, one will overwrite the other. Leading to potential cache misses. Again, I understand what is happening with the cache, but what exactly is block? What exactly is a block of memory in main memory? I hope it provides me a satisfying answer. In cache mapping, a block is the smallest unit of data transferred. Okay, got it. Yeah. So what is happening is that whenever cache takes some value from the main memory, it writes it onto the cache line, and if something else is borrowed again, then we are just overwriting whatever was previously there. So just it is just overwriting, right? And with overwriting with block, they just mean the maximum amount of value which someone can draw from main memory at once, right? Map to same cache line, one will overwrite. Direct mapping performance is directly proportional to hit ratio. Yeah, yeah, that is true. That is true because we are technically just um, we are technically uh, how do I say that? Because we are overwriting things, right? So we have to make sure that whatever we are overwriting is actually something which we did not really need it. So if we did not really needed it, then obviously that will not hamper the performance that much. So if how do we know if we really needed it? If is by looking at the hit ratio. So if hit ratio is high, then it means that the performance is high, right? So yeah, so that is I think how it is working. For example, consider a memory with 8 blocks and cache with 8 lines. Using direct mapping, block 0 of memory can be stored in 0, 1 can be 1, 2 can be 2, 3 in 3. When if the block of the block 4 of memory is accessed, it would be mapped to 0. Again, this is we are doing the modulo thing, so I understand that. The main memory consists of memory blocks, and these blocks are made up of fixed number of words. Again, fixed number of words. Okay, I will assume words means the bytes. What exactly is a word? Typical address in main memory is split into two parts. Index field, it represents the block number, and index field, it tells us the location of block where a word can be. Again, not really clear to me. Tells location of block where a word could be. Yeah, so block really is what I'm thinking. Block really is like a word like a page. Again, I worked on a NES emulator by myself. So in a NES emulator there was a concept for like zero page indexing. Like it uses something like pages. So I would assume that each block is like a page, right? Each block is like a page, and we are just offsetting into that page to find a specific word. I will write it somewhere. Pages, blocks, uh, by words for reference. Yeah, just so I don't get confused again. But yes, I think I should define block when I explain this to myself once again, and I should yeah, I think it is time to just write it once so that I can understand what it is. Again, block offset, I think I understand that it is same as I think this works same as the pages in NES. So I think I understand it pretty well. Again, only difference being that instead of being a main memory, this is cache, right? Cache memory consists of cache lines. These cache lines has same size as memory blocks. Again, this was okay. This was main memory. This was main memory, right? Again, so this is exactly like pages and all that. Only the thing is that it uses a different name. In cache, it is not so. I think I misunderstood that, but I think I can continue from there. The cache memory consists of cache lines. These cache lines has same size as memory blocks. The address in cache memory consists of block offset. This is the same block offset we use in main memory. Yeah, again, if we are copying a block at a time from main memory to cache, I think offset will have nothing to do with it. Offset will just remain the same. Apart from that, only thing which we are having changed is the index of it, right? In here, over here, we had index field. Again, a field is like a page which can be indexed, right? So there should be something equivalent of an index field here as well. I think the way it is called pages in main memory, it is called cache line in index, cache line number. So I think cache line is same as something equivalent to pages, I think, right? Tag is the remaining part of address that uniquely identifies which block is currently occupying the cache line. Tag is the name, right? Let me clarify this first. Index field and n bits tag and index. Again, block offset will be there. Index field s minus r bits. This is not clear to me, right? I will copy this. And what is not clear to me, let me just verify it for once. It represents, again, this is clear. I think this is exactly what I think it is, right? Cache. Not clear to me. How is the stuff written for cache memory any different from what was there in main memory? Fixed size blocks, yes. Example, four words per block, yes. Address structure in main memory specifies block number in main memory, specifies word within. Yeah, I have no doubts in this. This is not something which I have any doubt in. The doubt comes here. Again, let me verify it once. I don't want to be missing, like I don't want to be stuck in here, right? 6-bit address 50 is split into 4 index. And what is this? 5 is the index field and block offset. Is that it? 4 bit selects 1 or 16 blocks. index. Wait, again this is confusing me more. Yeah, this is confusing me more. Cache is smaller than main, so only holds subsets of blocks. Which main memory block is stored in cache line? Selects which cache line to check. Same as main memory. Tag index offset. Again this and this is these two are the things which I could not understand right. Did not understand. So what I think is happening is, again this when I think I understand this, then I see this and I don't understand really anything. Again I can see what this means, but when I look at this I don't really understand what even is this. What does this even mean? We'll walk through how the same 16-bit address is interpreted differently in main memory versus cache memory. Imagine main memory as a big bookshelf with 16 shelves. Yes, each shelf consists of 4 books. Yeah, and to find any block we will specify which shelf and which position. Yeah, that is not an issue. 16-bit address, bits 5:0. This means the bits from 5th, like so this is like we are having our 6 yeah exactly 6 bits address, and like the last 2 bits are specifically to tell which book we are specifying on a on whatever the shelf which we will be using, whatever the block we will be using, and the previous one was to just tell which block are we going to use. And over here in the cache memory, what is there is that tag tells which block we are addressing, right? Again we could be specifying all other blocks as well, so should it not be more? So multiple shelves can be mapped to same table spot. Tag which original shelf this is, which position on our table. Again which position on our table is that. So like tag so first of all we will look into tag, like where is that tag. When we know that this is the thing which we are looking for, we'll look for the index. When we know that, we will look for the offset. Tells us that this shelf is from group 2. 100 shelf 9, and this is shelf from group 2, table position 1. Now that we have a small table which can only hold 4 shelves at a time, we will need a way to specify which main memory shelf is currently on our table. position our table is sitting at. Again, I did not read this right, that's why it caused me confusion. But um, which shelf it's on. A way to identify which main memory shelf, which main memory block is currently on a table. Table cache, okay, sure. Which position on our table it's sitting at. Again, this does not really make any sense to me. Like, if you're looking for this address, right, if you're looking for this specific address, then will we, so like first two bits of this address, will it tell whether this address is present in our cache or not? A way to identify which main memory shelf is currently on the table. Again, I will be ignoring this, like this does not really make any sense to me. Way to identify which main memory shelf is currently on our table. Tag. Again, how long have I been going for? 1 hour 12 minutes. Yeah, leave it at that. Way to identify which main memory shelf is currently at our table. Again, which block is at our table. So when we write 2, is it asking like I did not understand anything at all for this. Yes, I did not understand anything at all. Did not understand anything at all. Like, this is very confusing. I will blame him actually. Huge library with 16 shelves, each shelf 4 block. Each book has a 6-digit ID number. So yes, this is fine for me. I understand what this means. Reading table. Your desk has 4 slots. Cache line. Each slot can hold one shelf from the library, 4 books. But many library shelves want to use your desk. Which family of shelf this is? Next digit. Which desk slot to check? Which book on the shelf? So what I am thinking is, we are going to look for we are aiming to get value from shelf 9, and what is happening over here is that the first 2 digits will tell whether The first two digits will tell which family of shelf is this. So it is telling like which set of blocks I am having, like blocks which are near to each other, right? So like um, which section of the library I am in, I can understand it as which section of the library I am at. Now that I know which section of the library I am at, which desk slot to check. Again, now that I know the section, in that specific section which slot to check and which book to check. So why different splitting? In library we directly find exact cells, 16 options. On desk we have check slots, check a slot, only 4 options. Desk. So we can go for 4 desks. Okay, now I think I understand that. So if there is 10, like if I am looking for this address, first it will check 10, is it there? If it is, then it will move on to here. If this is matching, then it is there, right? If this I can find these two things matching, then I think we know that the book will be there, and all I need to is check the index of that book, right? Is that it? We directly find shelf. On desk we check a slot, if like book is really there or not, like the slot where the book is situation is, if even the slot is there or not. I think that is what we are checking over here. If that slot is checked, if that slot is checked, then we are going to find that slot, and then we are going to offset into that slot. So I think now I understand what is happening over here. So like when we fetch a specific memory address, so in general, when we are at the main memory, we are directly going to go to that specific memory, but in cache we are going to check for it. The way we are checking for it is like we'll check the first 2 bits, which will tell if that specific portion of the memory is there or not. If it is there, right, tag is that uniquely identifies which block is currently occupying. So which one is the index? Identifies the block. So yes, the one which is going to identify it is the index. So what I am thinking is that the first 2 bits which we are going to search for will determine the index. If index for the memory location, and next of it, the next 2 bits will be telling whether for that index do we have that block or not, right? Which will be the tag thing, I think. The remaining part of address that uniquely identifies which block is currently occupying the cache line. So we have to so the next thing is the tag number, right? So for that tag, then we are going to check for the offset. So I think now I understand it well enough. So it is like little bit segmented, because when we look at index, we don't have all the index, we only have certain indexes, right? Am I right or not? I think I am. So I think that that makes it a bit clear, because it is going to take the same number of bits, right? So yes, I think I'm up for the time as well. I will be studying this right now, but I think I need to get some air as well, and I need to have some medicine and stuff. Like I have to get away from computer for a little bit. So I think this has been long, and I think I have gained my traction to continue for now. Like I can keep studying for 1 or 2 more hours till like 2 p.m. 2 p.m. I don't mean 2 p.m. Till 2 a.m. So I think I can keep going. Let me see how was it going. Yeah, I think I should end it right here. I hope you, again, I don't think that many people are really watching, honestly, but even if you are, and regardless of that, what I think is that these things are this activity is really helping me. Like even if I'm not completely finishing anything, I think it is taking me to a situation where I think um, if I continue with this, I'm getting a little bit more productive each time. So this is really helping me. So yeah, um, I think I will continue with a little bit more stuff tomorrow. But yeah, this was today was really helpful for me. So I think I will be